What is a resistor and what do they do? Let's find out. So let's get straight into this by looking at a resistor. A resistor is essentially just a piece of wire or piece of material sandwiched between two wires. This resists the flow of electricity, i.e. the flow of current, and there are several mathematical formulae and different applications for resistors, some of which we will cover today. Now let's start by having a look at a drawing of the outside of a resistor, such as this one in the corner. Now this is what a typical resistor looks like. You can also get solder mount versions, which are essentially just little rectangles with metal pads on either end. But for this video, because we're starting off simply, we're going to be looking at these through-hole versions. Now on the inside, if you actually scrape away all of the ceramic outside, which is this painted cocoon looking thing, you'll end up finding two little metal end caps, one on each side, that is directly connected to the wires coming out. And in the middle is an insulating material which is dependent on the resistance value of that particular resistor. They can be longer, thinner, smaller, wider, only ever so slightly, and it could be an entirely different material depending on the resistance value that you're looking for. Now, how do you tell what resistance value you're looking for? Well, you just use the little lines that are painted on the resistors. Now, as you can see, each line is a different colour in this case, and each line means its own number. Now, let's go to Narrator Me, which will show you what the colour code means. Thank you, Presenter Me. Not like I want it to work anyway, but... So say you've got a 4-band resistor. The right hand side of said resistor either normally has a gold or a silver band on it. That indicates the tolerance in this case, typically 5% or 10%. Now that means how much the actual resistance value varies from the resistance value indicated from the other 3 bands. So now that we know what the right hand band is, we can identify what the value is based on the left hand bands. So the first 2 bands are easy, they're digit 1 and digit 2. Now according to this table here, they start from 0 and go to 9, depending on the colour, so it's easy to just find out what colour is which stripe or which band and assign a number to that, then move to the band to the right of that and do the same thing again. For that's only for the first 2 bands making up the first 2 digits. The third band on a 4-band resistor is the multiplier, i.e. how many zeros you add or take away to the end of the first 2 digits in order to indicate whether it's kilo ohms, mega ohms, single ohms, or even milliohms if you're going that far. However, let me just quickly talk to you about the 5-band resistors. These are normally metal oxide resistors, and the first 3 bands are the digits, so instead of having 2 digits, this is 3 for a slightly more precise resistor. The 4th one is the multiplier, and the 5th band is the tolerance. Okay, thank you, Narrator Me. Now, what do we do with these resistors of different values? Well, let me tell you with some maths. Now, I know engineering is quite heavily mathematical, and I'm not particularly one for maths, but we'll give this a shot anyway because you do need to know. Now, the first formula that you should know is Ohm's law. And Ohm's law is like this. So Ohm's law is essentially that the voltage across a component is equal to the current flowing through said component multiplied by the resistance of that component, which is measured in ohms, hence Ohm's law. And you can also rearrange that into current equals voltage divided by resistance, and resistance equals voltage times current. Now, the main place that you use this equation, or these equations, is in either a voltage divider or an LED current limiting resistor calculation, which is slightly more complicated and won't be covered today because there are many calculators online that do it for you and many other tutorials telling you how to do it as well. Now, here is a second equation that is heavily used alongside the Ohm's law equation. And this is the electrical power equation, which is power in watts is equal to current times voltage. Now, this is useful for resistors because it determines how hot your resistor will get when a certain amount of current is running through it. Now, there is a variation on this, which is P equals I squared divided by R. Basically, you can use the resistance value of your resistor and the current going through it in order to calculate the power. Now this equation is the one more often used when you're determining the power needed for your resistor. Essentially, if you have too much power going through your resistor and your resistance power value or power rating is too low, then your resistor will start to get extremely hot and perhaps burn out entirely, which is what we are going to do right now. Now let's use the formulas that we have learnt today to determine a resistor which will get sufficiently hot and burn out without tripping our 1 amp 12 volts power supply. So let's write down what we know. We know that our resistance is equal to, and we don't know that yet. So what voltage are we working with? Well, we're working with 12 volts power supply, and the maximum current that we can draw, max, is 1 amp. Okay? Now, just because I don't want to break my power supply, I'm going to say that I, in this case, is only 0.9 amps, or 900 milliamps. Now let's use the power equation to figure out what power our little circuit is going to produce by taking our voltage and timesing it by our current to get the power. Therefore, 12 volts times by 0.9 amps equals 10 watts. So that's saying that our resistor, which I have only got 1/4 watt versions, is going to burn out very spectacularly. Now, what resistance value do we actually need? Now let's use R equals V divided by I in order to find out. Our resistance value that we need is equal to 12 volts divided by 0.9 amps. So our resistance value that would get us exactly 10 watts of power is equal to 13.333333333 ohms. Okay? Now, that is a very ugly resistance value. So we're going to choose from either 12 ohms or 15 ohms. Now 12 ohms would give us a current consumption of exactly 1 amp, which is over our threshold that we wanted to establish earlier. So we are going to use a 15 ohm resistor instead, which should still get sufficiently hot. And it just so happens that we have a 15 ohm resistor here. Take your power supply, take a female connector for it, and it's as simple as putting the resistor across it, and it should get sufficiently hot and burn out. But we're not going to do it by just connecting the wires, because, well, it would probably burn my fingers, and we want a good camera angle. So instead, we are going to use a breadboard, but the principle remains the same. Just connect the power supply across the component, the resistor in this case, and let electricity do its magic. So as you can see, our resistor is just connected straight up to our power connector, and as soon as we plug that in, this resistor here will start to get very hot, and you will see it. Are you ready to see this burn? Let's go. Isn't that just beautiful? Now let's do that again. Now, let there be light. Oh, oh, that's a lot of smoke.